Inductors have a symbol of a coil, and they have an inductance L that is measured in henries, abbreviated as capital H. The inductance is a property of the inductor, and it's based on the geometry, number of coils, etc. Naturally, an inductor will resist changes to the magnetic flux through its loop. Consequently, inductors will resist any changes to current through themselves. We'll look closely at how this works. An ideal inductor would have no resistance, but since inductors are actually made of thin wires, there will practically be some resistance in real inductors. Let's look at what is called an RL circuit. L is the symbol for inductance. So we have a resistor and an inductor in series. Let's assume that the switch pictured below has been opened for a very long time, and let's assume there's no potential difference across the inductor. We want to label important voltage values around the circuit when that switch is open. I'll start off by connecting the negative terminal of the battery to the ground, and we'll consider that to be 0 volts. Naturally, we'll also have 0 volts on this side of the inductor. It was given in the instructions that the inductor had no voltage across it at the current time, so that would mean that this is a 0 volt potential as well. The switch has been opened for a long time, and we'll assume that no current is flowing. With that in mind, we would have 0 volts at this point and 10 volts on the other side of the switch. So the entire potential drop in this case would be across the switch. The instant after the switch is closed, what will be the potential difference across the inductor? And what is the potential difference across the resistor? So one thing we might want to do is think back to the past and how we had looked in depth at circuits involving resistors in series with capacitors. That was called an RC circuit. And as soon as you close an RC circuit, there would be a potential difference established across the resistor. So we would have 10 volts here, 0 volts here, and it would really take time for the potential difference across the capacitor to build up because it was all based on the charges that would flow onto the plates. There's some similarities here with RL circuits, but there's some major differences too. Inductors resist changes to current. Let's think about that for a minute. Before, the current was definitely 0 because the switch had been open for a long time and equilibrium was established. So if the inductor tends to keep current from changing, then we should still see 0 current right after the switch is closed. And it'll take time for current to build up. So what does this mean for the voltage around the circuit? Well, we're definitely going to have 0 volts at this point. But we don't want the potential drop to be all across the resistor at this time, because as soon as the switch is closed, we won't have current right away. It'll take time for the current to build up this time. With an RC circuit, current started flowing immediately. We're going to have 10 volts here, and we'll actually have 10 volts at this point as well. So all the potential difference initially is going to be across the inductor. That's one of the major differences between an RC circuit and an RL circuit. Now, if the switch has been closed for a long time, what will the potential difference across the inductor eventually be? And what will the potential difference across the resistor be? All right, so we've got 0 volts at the negative terminal, 0 volts here, 10 volts here, no question about that. But how much voltage at this point now? The thing about inductors is they don't prevent current from flowing absolutely. Eventually, current is going to be allowed to flow. It just takes time to build up, though. But if it has built up, then the current will flow as normal, as if the inductor wasn't even there. So since we need normal current to flow a long time after the switch has been closed, the voltage that we need here needs to go back to 0 volts so that we have a potential drop across the resistor, and then current will flow through it. At this time, the inductor won't impede current anymore. Taking into account what I showed, let's sketch a graph of current versus time for the circuit shown, starting from the instant that the switch is closed. We also want to draw the resistor voltage and the inductor voltage versus time. So the type of graph that we'll get for current will be a graph that builds up to a maximum, starting from 0. It'll take this shape. It's worth noting that this is the opposite of what happened in an RC circuit. In an RC circuit, current started up high and it decayed to 0. But for an inductor, the current will start down low and build up to what could be called I max, the maximum current allowed. Now the resistor voltage will actually just follow current based on the same principles that we had seen before. So that as well is going to build up to a maximum. The maximum that it builds up to will be the voltage of the battery. But what about the voltage of the inductor? Well, I said that inductors will start up high with their potential difference, and over time it'll decay to 0. It'll start with a voltage equal to the battery. In order to show that there's a transition from inductor voltage to resistor voltage, we could write Kirchhoff's loop law for this circuit. We would have 0 equals the voltage of the battery minus the voltage of the resistor minus the voltage of the inductor. Now the voltage of the battery is always going to be 10 volts. So what this will show, if we solve it, is that the sum of the voltage across the battery is always going to equal the sum of the resistor voltage plus inductor voltage. Here are the formulas for LR circuits. Very similar to the formulas for RC circuits. But of course, the forms of them have been reversed in order to reflect the new type of graphs that we'll have. So the formula for current will be I as a function of t will equal I max times 1 minus e to the negative t over tau. And tau is the time constant for the LR circuit. Very similar to the time constant for an RC circuit, but we use the inductance L instead. Now this is the formula for building up current in an LR circuit. The form of it is reversed when we're disconnecting the circuit and decaying the current. For voltage across the resistor, when we're first connecting the circuit, we'll have VR as a function of time equals V max times 1 minus e to the negative t over tau. And once again, we're building up current in this case. For the voltage across the inductor, we'll have this. So those are the formulas we're going to want to use with LR circuits.